Hello everyone, it's Logan again, and today I decided to take apart the motor that I showed you last time, give you a good look inside it, and explain a little bit about how electric motors work and some of the different designs that you can have inside an electric motor, why we need them, why we want them. And to start off answering that question, I wanted to explain the simplest definition that I could think of for an electric motor is something that uses electric current or moving electric charges to create a torque about a central axis. And there's a couple different designs you can have for that. One of the reasons you might want that is to do some sort of useful work. For instance, this drill has an electric motor in here that spins. It creates a torque which ends up spinning the bit, which can either drill or screw or unscrew, so it can go both ways. And of course, this is actually a pretty complicated one when you think about it. It has a bunch of different settings. It can go forward and backward, high and low torque, and it's all very compact and uses a battery. Well, if you remember last time, I showed you the very simple motor. You can get that on simplemotor.com. It's really, really neat for showing how electric motors work or how they go about creating their torque, but it doesn't really explain how to build one to do something useful. So there's really two, at its most core level, there's two different ways that you can make it. The first way is the way that the majority of motors were made for a long time, which is like this. It has a central rotor, so basically this shaft here, which can spin, that's in the middle, and the stator, which is the part that doesn't move, is on the outside. And for a long time, that's how all of them were made. But then someone ended up deciding to go a different way. They ended up creating what's called a hub motor or an inside-out motor, which is like this, where the rotor is actually the outside part, and the stator that doesn't move is on the inside. You'll find this design in a lot of things like fans, either whether your overhead kitchen fan or your computer fans, hard drives use them. They're nice for being CD-ROMs use them. They're very compact and they can create a lot of torque and a lot of speed that way. So why did I decide to go with this? Well, the majority of electric cars are actually using something closer to this, far more complicated than this, but they're using something central because it can interface very easily with a transmission. So just like an internal combustion engine, it will spin around the outside, spinning a central shaft, and that shaft can be hooked up to a transmission for gearing and then output to the wheels. So it can actually be dropped directly into a car that you have now, assuming it can output the right amount of torque and horsepower. There's good and bad things about this design. I went with it for a couple reasons. One of them is that it tends to create a lot of torque, and personally I think it tends to look a lot cooler. It's also a lot more of a challenge for me to build. Some reasons why you wouldn't want this in an actual car would be that it leads to what's called unsprung weight. Any weight that is not resting on top of the springs reduces handling and ride performance in a car. Now, of course, it reduces the amount of space that has to be used up inside the vehicle for the motors, which is a good thing. But one of the downsides is that it is much more difficult to hook up to a transmission, although there are some that will use planetary-style gearing inside the motor itself, which, of course, is really, really complicated. So how does this all go together here? Well, I made this out of MDF because this is a prototype. The final version will probably be made out of aluminum. But basically there's a bearing inside here that spins, that gets connected to the shaft itself. This is to actually connect it to the motor. Now you can see right now that it's basically attracted to the magnets because there's steel inside here, inside this stator. Once this is on, all the screws connect and it holds it up, and they end up staying kind of right in the middle. I don't know if I can do this with one hand. There you go. It's about 1/8 of an inch, maybe 3/16 away. One of the principles that'll really help make it more powerful is that the closer you can get, basically the smaller the air gap, the less magnetic field you're losing out to the air. So the closer the tolerance is, the more powerful the motor is going to be. One of the ways they do that is by actually having curved magnets instead of straight ones. Now, I end up using just square magnets because they're a lot less expensive. I did end up having, for this regular shaped motor back here, this is the very first prototype I made of anything as I was learning how to make electric motors. And you can see, yeah, it's pretty tore up. You can see I was experimenting with different gauges. This is, I believe, 26 gauge wire, same thing as I'm using in there. No, I'm sorry, that's 30 gauge wire. And this is 20 gauge wire. And so I was experimenting with the difference between there, how much torque, how much horsepower it would output, speed, and so forth. But inside there would actually fit this. I had these magnets custom made from a supplier in China. It worked really well. I had it up well over 2,000 RPMs, 2,500 RPMs, which puts a lot of force on it. I was getting a little bit worried there. That's why I taped it, because I was getting a little worried that it might fly apart at some point. But it was going pretty fast and really not drawing that many amps at, I think, only 12 volts. However, a proper motor is going to be using steel for a stator. Why are you going to do that? Well, electric current goes through these wires. As it does that, it creates an electric field inside here. Iron and steel tend to enhance that magnetic field, which is why you use them in solenoids as well, which means it will actually interact more strongly with the magnets. Now, technically, you can use any old metal at all. You could find a bolt and wrap coil around it, and that would enhance the magnetic field. However, there's a couple downsides to that. One of them is something called hysteresis, and another one is eddy currents. So as the current runs through the coil here, what it does is actually create an electric current running through the metal in between it, and induces an electric current in there. One way to stop that, or reduce it, I should say, nothing will ever completely stop it, is to create a motor that's in laminations. So, let's see how well you can see it. There's actually individual sheets of it, there you go. Individual sheets of it that are layered together so that the current can't pass through one to the next. So it significantly reduces the way the current can flow and how much current is capable of flowing through. You also want high electrical resistance in the material itself, so you don't get very much current flowing through it, and therefore you're not wasting very much current or creating extra heat inside the stator itself. Now, the other thing is called hysteresis, and that's something that I can't really demonstrate to you just showing this to you, but hysteresis is like a memory effect. So when these get magnetized, what happens is all the little pieces of iron inside there get aligned. They all point the same way. And that's why a magnet can be so powerful. The more of those that point the same direction, the more powerful the field is. But it tends to remember that. All those tend to stay aligned for a fair amount of time. Well, if you're turning on and off the motor every time these Hall sensors tell you to, which the Hall sensors are on the other side of this, of course. I'll see if I can pull it out here in a minute. But whenever those Hall sensors, like I showed you last time here, whenever these sensors tell you to turn off the current, the magnetic field is supposed to go away. But if it remains, it can have an adverse effect on the performance of the motor itself. So this particular metal is a silicon steel. Not only does the silicon steel, the way they make it, tend to enhance the performance, the magnetic field, they also are resistant to hysteresis. So they lose their remembrance of the direction of the particles are facing very, very quickly. So they don't get stuck in this. And that's even more important if you're using an AC motor, which is actually changing directions versus just turning it on and off. But either way, that's what you want. So I actually had to special order this metal. They sent me a whole bunch of sheets of it. You can see right here, I've already used quite a few of them, but they wouldn't cut it to the right shape in each lamination, so I'm doing it myself with my trusty Dremel tool here. And I've gone through a few of these tungsten bits. Let's see if you can see that there. There we go. It takes a long time, but it's really the right way to do it. Now, of course, businesses, if they're making these to sell, they're going to run off, say, 100 motors at a time or 1,000 motors at a time. And so if they have 50 or 100 laminations, that's 50, 100,000 pieces of this. The cost of getting that done is actually pretty reasonable. But when I shopped around to have it cut by a laser cutter or water jet cutter, the cost was ridiculous. I mean, for one of these stators here, it was something like $600 or $700 on the low side. And there's one that was well over $1,100. So yeah, making 1 to 4 of them just for my little home purposes here wasn't really useful at this point. Okay, so now I've disassembled, at least partially, the motor, and you can see the other side of it. Yeah, I know there's still a lot of tape. It's a prototype. But these right here, those are the Hall sensors that I was just showing you. There's 3 of them. There's one for each phase. Let's see if I can get you a better view of it here. And I've glued them in place. It took a lot of experimenting, moving these back and forth, figuring out exactly where they should be. There is math that you can do to tell you exactly where to put these, and it has to do with mechanical degrees versus electrical degrees. I believe there's actually 2 electrical degrees in every mechanical degree, so if there's 360 mechanical degrees in a circle, there's, I believe, 720 in an electrical circle. That being said, I used some of the calculators to figure that out, and it wasn't really coming out right, so I must have been using it wrong. But this is a 3-phase setup. Now, what is a phase? Well, the simple motor I showed you before had 1 phase to it. Basically, 1 coil, 1 sensor. It would turn on and turn off, and that was it. It spun the motor. And for that simple motor, that was really all you needed. However, it doesn't start up by itself. If you remember, I had to actually spin it first before it got started. So in order to make something spin by itself all the time without fail when it's starting up, you have to have at least 3 phases, so that no matter what position the magnets are in, at least one of them, or 3 in this case, will always be in the right spot to have a torque on it to start it spinning. And once it starts spinning, then the other 2 will always be able to kick on correctly. So that's why you want to use at least 3 phases or multiples of 3. You can have 6, you can have 9, 12. It doesn't really matter. It just depends on how big the motor is. Now each of these, I believe I wrapped each one of these 50 times. So the wire is going around here. And in a later video, I'm actually going to be doing a more close-up look at the math to figure out, how many turns do you need. One of the balances that you have to create is, do you want more turns of a thinner wire, or do you want fewer turns of a thicker wire? So it's a balancing act of which is better. And it really depends on application specific. So that's why I was doing all these different experiments with different sizes and configurations of motors. You can see this one back here. So it actually had 3 coils per phase, and it had 6 phases or 18 different ones. Well, why did I do that? Well, just to experiment. And there's good things and bad things about it as well. It's probably a little bit more accurate if your machining ability is not up to snuff like mine. Now, again, the reason I was experimenting with MDF board is just because it's easy to prototype with, but it reduces the properties of your motor significantly without having the steel in there. But rather than spend all the money for steel and all the time creating laminations when I didn't know exactly what form I wanted, I ended up doing this. And that's way I could still experiment with different numbers of turns of wire and different gauges of wire and so forth. Okay, now one more thing to be careful about when you are building something like this is that all of these edges need to be electrically insulated from the wire, because if you ever get, and this has happened to me, if you ever get a break in the insulation around the wire, it's actually going to conduct current from the wire into the stator itself. And that can short out your motor, it can draw extra power, reducing the lifespan of the batteries. It can also add extra heat, which can be detrimental. So you want to make sure that these are electrically insulated from one another. And most commercially produced motors actually use some sort of a special paper that gets wrapped around here that the coils then wrap into. And a lot of times they can actually machine produce the wires, the coils into the stator itself. And they're packed very densely. But there are, of course, limits to how they can do that. So in an inside-out motor here, all the wires have to go through the hub. They have to go through the shaft itself. So you can see they're coming out the end, and there's two sets. There's the sensor wires and the actual power wires themselves. They're going to go on to connect to the actual transistors or MOSFETs themselves. Now there's a couple ways of controlling this. One is through changing the voltage. So you can have a switch that maybe switches from 12 to 24 to 36 volts. But unfortunately when you do that, you lose some of the torque that the motor is creating and the horsepower itself. The other way is to use what's called a PWM, or pulse width modulator. And by turning this from 0 up to the maximum, I believe this one is 25,000 hertz maximum. Every time it pulses, it sends the current through and then shuts off. So the positive thing about this is that you can have maximum voltage at all times, and you can pulse the current into the motor to limit the actual amount of torque that it's putting out, or rather the amount of power going through it. So you can get a slower speed by pulsing it more slowly. The downside is that you actually have to be able to handle the current. So I believe this one can only handle 10 amps. So it is not capable of withstanding all the current coming out from 9 different MOSFETs there. Or transistors, I mean. Now one other thing I wanted to talk about is the kind of wire I'm using. Any insulated wire actually works, but the most efficient kind is what's called magnet wire. And you can get it in various colors, various gauges. I get all mine off of eBay. This is, I believe, 24 gauge wire. I think the blue looks particularly good. I ended up going with 26 gauge, but the whole reason I'm making that other stator there is to be able to test with a different gauge of wire again, 20 gauge in this case. So I won't be able to fit as many turns, it won't be as efficient, but it can carry a whole lot more current. And it has a lot less resistance to it as well. So you can get this stuff off eBay in a ton of different lengths. Very, very useful. And the other neat thing about it is that all you have to do is on the end of the wire. Let's see if we can get a good example going here. I don't know if yeah, I think we can see that pretty well. There we go. So you can see where the green insulation itself is. That's actually an enamel. And then over here at the end, I've actually scraped it off. You can use a scissors or a razor, just about anything. I used a lot of times X-Acto knives. Works really well, and they just scrape off the insulation on the part that needs to be able to conduct. And of course, this is one I've used from a previous thing. It's got some solder on the end of it. Then you can either twist them or you can solder them to whatever connectors you need. Now right now, I'm using a lot of alligator clips. But in the future, I'm going to be using these, which are actually 6-pin PCIe connectors. You can solder them on there. I am not an expert on soldering, I'm sure you can see. But it's actually pretty simple once you get going with it. And this way it'll be real nice and easy. The coil wire is going to have a 6-pin, and so is the sensors, so each one is going to connect in here, and then these will connect directly to the wires coming off of the power supply. So it'll make it real easy to connect and disconnect the wire on the fly if I need to take off the motor and diagnose it as I'm driving around. All this is eventually going to be a little go-kart. I don't know that I'm going to use these tires. It'd be nice to get actual go-kart tires, but bigger tires spinning at the same speed will end up going faster. So that's something I still have to experiment with, but I think we're just taking this journey together here. So eventually I'm going to have a little go-kart to run around with. That's the video. Thanks for checking it out. I do plan to bring you more about the way these motors actually work, how to design and build and calculate what you need, and of course the different types, different possible designs that there are. So thanks for checking it out. Like if you like it, subscribe if you want to see more, and of course let me know what you want to see, or if there's anything else I can do better with the way that I'm presenting. So have a great day.